Okay, I'd say let's start. Maybe one or two will still appear, but we can start here. So I've updated the web page a bit. I made a fancy title line and so on, but especially I uploaded the video of last lecture in case somebody missed the lecture and wants to look at it. Unfortunately, there's some whistling sound, so I don't know if it's very good to look at. More interesting, I've updated here the write-up for the principal component analysis. You know, this is up to here. I've showed it to you in the lecture. And then I showed you the rest on the blackboard. And I've decided just to have it for the future to type all this from the blackboard here again on the this screen. Also, when we had the lecture, in a way, we didn't quite go full circle and didn't really look at how the projection that we then get on our PCA can be used. Because you remember we talked about how we use the eigenvalues of the covariance matrix to see find the projection. But we haven't yet talked about how the projection serves as a rotation. That's a bit what I wanted to do in the last lecture, in the last exercise class, but we all had this strange problem with everybody's RStudio, including mine, kept crashing. I still think it's a bug with the way how sparse matrices are indexed, because I tried it afterwards with really a minimal test example, and half of the time my computer crashed and half of the time it didn't. So it's one of these annoying Schrödinger bugs where you never know how to reconstruct them. I hope somebody else will solve it and make a proper bug report, and this vanishes in the next thing. But as you might have seen in the exercise that I gave for you over this weekend, I have constructed an example with a really small matrix where there's no risk of anything crashing, and we also probably show how this actually works as a reconstruction. So in that way, if you haven't done it, we'll talk about it tomorrow. If you have done it, even better, then you can see this. We also have here the modularity clustering we talked about last time, which I think is, sorry, this wasn't what I wanted to look at. Here, this write-up we went through already last time, but yeah, I also uploaded it because I'm not sure it was online already last week. So if you want to look something up, which I showed you and I've forgotten to upload it, just send me an email. I keep not noticing that something might be on my computer, but not on the web page. Now for the homework, yes, as I said, I made one homework on modularity and one on PCA. Let's see if, of course, my hope was that you look at maybe at a few parts of this and not go through all of it, unless you're really motivated, then of course that's also great. So let's see how far we get with talking through this homework tomorrow. For today, I want to talk about trajectory inference, because, you know, biology in the end, these are dynamic processes which we want to describe. And a lot of biology and a lot of science is dynamic processes. And you can talk a lot about how you describe the dynamics of a process, what controls it, but before you can do, you have to describe the kinetics. You have to simply show how do the cells change over time. And for this, we will now start looking at a way how to describe this, and we will come over several mathematical issues which we need good solutions for, which we then look at in time. I don't know how far we get today, probably most of it will be next week. So maybe here, if you want to look at it, I've labeled it here trajectories, but I've also loaded it here. And we can start here. And what I now will do, I use the same data set that I always use of this neural stem cell data set. and run it through a standard server analysis. And now while this thing runs, we can also show you where we get. In the end, we get to this UMAP plot. And here, as you can see, there is here a long continuous thing, and then there's all these surrounding clusters which are isolated. This long continuous thing, we will call the lineage from now on. Maybe a bit unclear name why we call it the lineage, but that's what my biology colleagues always call it. And this lineage is basically down here. These are the neuronal stem cells. And I told you these neuronal stem cells, they just sit there, sleeping or being dormant or quiescent, as they call them, QNSC for quiescent neuronal stem cells. When they get activated for one reason or another, and then they sit here, and then they start amplifying, so they make copies of themselves, and for making copies, a cell has to go through what's called the cell cycle. The cell cycle is this cycle of 4 phases. First, the cell takes up nutrients, grows, and so on. When it duplicates its DNA, so that it has all DNA strengths in double the number, then it prepares to divide, so bring something in, moves what's called the mitosis, where the 2 copies of the DNA are pulled to opposite ends of a cell, and then in the middle the cell divides, and then you have 2 cells. And then each of the 2 cells can again start dividing. Now, if you have a single-celled organism like a bacterium or a yeast cell or something like this, that's all they do. I mean, they want to grow, and growing means taking up nutritions in order to divide the cell, and so these cells, they go round and round and round. In a multicellular organism like an animal or a human, cells mostly don't do that. You don't want your cells to keep dividing. You want them to divide only when it's necessary. Like when you grow, of course, the cells have to divide. When you injure yourself, the cells have to divide. When cells get old and needs to be replaced, they need to divide. But in general, you don't want them to divide. And as important that a cell starts to divide when you need new cells, but equally important it is that the cells stop with their division once there is enough cells. If the cells don't stop with their division and they keep growing and so on, you grow a tumor. And this is what we call cancer. Cancer is the disease that cells stop dividing after they have started for whatever reason. So in our case, what we have here is the stem cells get activated when they make a few rounds of division, and when they go on, make maybe 3-4 rounds, so that each one stem cell turns into 16 daughter cells, and when these things change shape, become this typical shape of neuroblasts, so the precursor of neurons, and finally they turn into neurons. What we see here is, of course, not one cell doing this, but we see many different cells which are on different stages at this journey. So the idea how we interpret this plot is that we say there is a dynamic process, and this dynamic process happens all the time in some kind of steady state flow. And if we take a snapshot at one given time, we will find cells which are at the beginning of this, cells which are still a little bit further, and cells which are at the end of the process. And cells which are similar far advanced in this process are probably also next to each other. So we are tempted to say this is probably the direction in which this whole process goes. The cells start here. A cell here will turn into a cell which looks like this, which will turn into a cell which looks like this. So in our big PCA space, we have sort of a flow along which the cells flow along in order to turn from an initial state into a final state. Yeah.
You mentioned PCA, but do we have reason to expect that different directions will always preserve this limit? We always have this?
No, we don't. We only have part of, but we will check this in a moment whether this is the case here. So what we do for that is, first we need to orient ourselves in the plot. And we have here this thing, and when I looked at this, I didn't even remember what was the start and what was the end. But I did remember when there are certain genes which are typical for the start and the end. Aquaporin 4 is a gene which is expressed in astrocytes and with stem cells. MKE67 is a gene which is always expressed when a cell is dividing its DNA. Double cortex is expressed in neurons, and in developing neurons, and GRIA1 in mature neurons. So I made this feature plot function, which, as you remember, just colors the points in the UMAP by the strength of the expression of these genes. And now it's easy to see the start point is up there, it goes down here, and here's the end point. So when I showed you before, I did it the wrong way around. We start up here, go through that, and end here. We could also, let's first go, let's first do what you've just already said. Are they really connected? We can use the sleepwalk tool, which, as you might remember, shows us these cells and colors every cell according to its distance to the cell under the mouse cursor. So we see all those cells here, which are now under the mouse cursor, they are really close to each other. So this is among the closed cells. If I now put my mouse here, then I see these are among the closed cells. And that way I can now go through this and can check, okay, this looks like maybe here. Now it's not so clear. From here I jump here and maybe here. So now I've avoided the cell cycle, or maybe I go that part, go here, here. You see, I always try to go from green to green so that I make only small steps to convince myself that I will follow this thing, and then I end up here. Interesting enough, I will also notice that here the UMAP has done a bit of a mistake. You see the end here of this big blob and the cells under my mouse, they seem to be quite close to each other and might be connected. This here is the simply Euclidean distance in PCA space. No, in the PCA, the color is according to distance in PCA space.
Okay, and that's why it's not Euclidean distance within the UMAP.
Exactly. The Euclidean distance tries to find a 2D projection which makes the Euclidean distance in the UMAP sort of similar to that in the PCA space, but this doesn't really work well, and that's the whole point of this tool, to allow you to check that. And you see it more or less works, but here it's somehow strange. This thing, what happens here is that these cells seem to be very similar to those, but you can also see the different speeds here. This here seems to be all quite close, while here I make much smaller steps from green to green. So this here is a rather small area in PCA space, while this is a rather long way through PCA space. And here it's again small, and here this almost seems to be a jump to go to here. Could maybe put this a bit further up. And here we see a lot of is changing here along this space. We will later at some point maybe talk a bit more about what this UMAP really does. The thing that I should say already now is UMAP works on the neighborhood graph. So the first step that the UMAP algorithm does is it does this neighborhood graph that we talked about last time and connects each cell with its 20 nearest neighbors. So if there is a big jump and a cell jumps to another cell, then this fact that this is a big jump will be lost, because the UMAP algorithm only says, well, this cell is a neighbor to that cell, and that cell is a neighbor to that cell. And it tries to find an arrangement with 2D plots so that the neighbors are close to each other. And whether the neighbor was now close or far away, that part gets lost. In a way, this is intentional because, as you've seen here, sometimes the jump is by a factor 100 larger than another jump, and you essentially would have a picture where this here would be a really small area in the plot, and this thing would fill the whole plotting space, and you wouldn't have a nice overview. But it's important to keep in mind that it does that UMAP completely distorts the length scale. So, here. Okay, what I also wanted to check here, but let's skip over this, is what's this. So I've decided to completely ignore now all these small clusters and only use the big lineage and add this cluster 7 to the lineage because, as we've just seen, there seems to be a jump from 2 to 7. Also 7 expresses the mature lineage marker, and this here expresses the immature neuroblast markers, so somehow this should be connected. This here are oligodendrocytes, and when I wrote this up already last year, I was wondering what it is, so I quickly double-checked and asked it to make a comparison between the genes in cluster, in all the clusters along this lineage, or in cluster 4 or 8. So let's call, as I said, we call this here the lineage. So here I have now set all these clusters 10, 9, 0, and so on. So these are all these here 10, 9, 0, 13, 14, 3, 5. This is the lineage, and 7 as well. And these two things out here, let's call it 4 or 8. And we can ask this thing here to make a Wilcoxon test to compare which genes are very different between all the cells in the lineage and all the cells in this extra cluster 4 or 8. And here you see which cells I got that way, which genes I got in this way. And then I was wondering, what are they? What I actually did back when last time I got this list of, here it's only 10, but I think in total, because I cut it off and only showed the top. But overall, this was 30, 40 genes, and I wasn't quite sure what these genes are. So I just put them into ChatGPT and asked it, what do all these genes have in common? And it actually said, as I also remembered when from what my biologist colleague said, that these are oligodendrocytes, which is another cell type in the brain, which has whose purpose is to make the myelin sheaths around the neuronal connections, which are important to have fast signal transduction. But that's an interesting piece of physics, but we don't need it here. So let's go on and check how now this pseudotime is. We have now said that with sleepwalk we can see how the trajectory goes along here. And now one way to find this trajectory is to make what we call a principal curve. Imagine you have in some space, point space which has some banana shape, something like this. And now we want to find a curve, and this curve, which sort of connects all these cells, something like this. This curve we call a principal curve, and we define it as follows. We try to find a curve such that the distance of every point to the curve, so always to the closest point on the curve, is as small as possible, as usually in the least square criterion. So we add up the squares of these distances and say we want to find a curve which minimizes this. Of course, one curve which brings it to 0 would be that one, which just goes to everything, that it's a very wiggly curve. So we also make some penalty and say we want to minimize it without making the derivative the second derivative, so the curvature, too large. So that's something you have quite common in these optimization problems, that you do that you have a loss function which you want to optimize, and the loss function shows a trade-off between two things. Here the loss function might be the sum of the square distances of a point to the curve, and the loss plus the integral of all the curvature along the whole curve. And you say both of them have to be small because you want to minimize both concurrently. In practice, how this works in detail, we will talk about later. For now, it simply means if you have a lot of dots of data points, which are now not just a big blob, but which are arranged in your feature space, your PCA space, in some long elongated fashion, then you can find a curve which goes through the middle of all these points, like this curve here goes through the middle of these dots here. And in this case here, of course, we might be tempted to say, okay, what might be a good curve which follows through the PCA space here, this line. If we do this, then these things make it a bit different with cell cycles, or you're better off fitting a curve only through this here for our first attempt. So I remove these two clusters. That's what I have done here. So the cluster 6 and 11 I remove. And then I get my listed clusters 2, which are all the clusters in the lineage, except for rows here. Where have I put this here? Exactly. And now lineage clusters are these here. Now, as I will talk at length about in next week or the week after about how this principal curve works that I've just shown you here, because it's a very nice piece of math. But for this, we first have to talk about smoothing. So I turn this around, because for smoothing, I need a principal curve to have a nice example. So you will see why I do it in this order. So for now, I simply call this principal curve algorithm. That's no new thing. That's been written in the 90s, this function. And as you can see, it takes our PCA coordinates only for the cells which are in the lineage and finds a curve through these PCA coordinates. I think it does 10 iterations, so it should have finished by now. And here, I think this number here is the sum of squares of the distances of each point to the curve. 9, 10, okay. So, and what I get out of this from this thing is then here this PRC object, which, as you can see, has here a slot S. I can also show you here, which is a big matrix, 14390 by 20, which gives for each of our 14,000 cells the closest point on the curve. Obviously, because our cells haven't been in the right order, we also need to know which point on the curve is. So the cell which was first in our input matrix is on position 6400 if you arrange all the cells according to their position on the curve. So each cell, this cell, for example, has now this position on the curve, and we can, of course, give it some coordinate by saying how far is it from the starting point, and by this we can order the cell. And here you see for each cell its place in this ordered thing. Lambda is the distance from here to a cell. So for example, if I have this cell here, I can say, yeah, let's draw it like this. Imagine we have points like this here. When I can find a curve such that if I project them onto it, the sum of these squared distances are small, and then this gives an order of the curve points. It can say this is cell 1, 2, 3, 4, 5, 6, 7. And I also can give each cell a distance which tells us how far away from the start point is. For example, for this cell, it would be the length of this curve, simply by integrating along that.
This is distance in UMAP space, not PCA space.
In PCA space. Everything in PCA space. We always do everything in PCA space because that is still a linear operation from our original data. The UMAP space is only for visualization, but we never do any calculation in UMAP space. We only use it for visualization. Of course, here now, for my example, I draw it in a 2D space, but you have to imagine that these points are points in a 30-dimensional space, and the curve goes through the 30-dimensional space. And yes, and now every cell gets a distance from the starting point, and we will call this distance the pseudo-time. Pseudo-time because our idea was that all the cells go along this trajectory. They start somewhere here, and then they evolve, and in the end they're somewhere here, but we got a snapshot where we just get cells at different places along this progression, and a cell pseudo-time tells us how far along the whole progression does this cell seem to be. And using this now, I can now assign to each cell such a pseudo-time. And I'll show you how this works. First, just to see a bit of, so here this are these lambda coordinates, these pseudo-time coordinates, which are the distance along of a projection point from the start of a curve. The n-frame command that I have here just turns this thing into a table. Now here the cell name, and here the lambda value. And here these are my PCA coordinates. No, these are now the UMAP coordinates because I want to show it to you. So what I have constructed here is simply a table which gives next to each UMAP coordinate the lambda value of the cell, and NA in case it wasn't in the lineage. And now I can plot this. And now I see my UMAP again. And on this UMAP, I now see here which pseudotime was assigned to each of these cells. And we can see that the principal curve seems to start here and seems to end here. And each cell got now assigned a pseudotime which tells us how far the cell's projection onto the curve is from the starting point of the curve. And this now brings our cells into some ordering, and now we can ask what's changing in the cells while they turn from stem cells into amplifying cells into neuroblasts and then finally into neurons. So we can pick a gene and ask how does this gene change along this smooth trajectory. And before we would have, with the modularity clustering we did last time, we would simply calculate the gene's average for each of these clusters. Say, okay, first the average is this, then it's that, and then it's this. But this is not so appropriate if we follow a smooth process like this one, so we better do it like we do here. Before we go a bit further, what I now first do is that I assign to the remaining cells also a pseudotime, and what I can do here, I have here all the points on the curve, each cell's projection point on the curve, and here I have the PCA embeddings of all the other cells, and I can use here this nearest neighbor function. Not sure if I mentioned it last time, but if you have a big data cloud and you want to find for each data cloud, for each data point, it's 20 nearest neighbors, then of course, typically, you might want to use, yes, right, I showed you this functional nearest neighbor, where it always makes a hyperspace to divide it into two, and in that way it divides up the whole space into different compartments to make it easy to quickly find the neighbors. So I call this functional nearest neighbor function and says, for all these points, I want to find the nearest neighbor among those points, and only the very nearest neighbor, only the first nearest neighbor. If I do this, then what the thing now does is that for every cell, it gives me the nearest neighbor on the curve. And of course, if a cell is on the lineage, then it will, here, for example, the fourth point will be close to the fourth point on the lineage. There's 3 here because the lineage seems to have numbered its cells by 0, while the first cell wasn't in the lineage, so it gets added somewhere. And with this, I can now again assign to each cell a pseudotime by just giving the cells which haven't had a color here, all the gray cells, I just give them the same pseudotime as the cell which is as the cell that it's closest to this cell's projection point. And then they all get similar, then all these here get similar values as that one, and these here get similar values as that one. We've also changed here now the direction, because here you see the pseudotime starts at the end and ends at the start. So I turned this around and said it should start with 0 here, and then it should go to the end here. And I can also ask, does this even make sense to project these points onto the curve? Maybe they are very far away, and if a point would be down here and I project it on this curve, it's more or less random where it ends up. So let's double check this by calculating for each cell the distance of the cell's PC coordinates to the curve. And we can do this again with the nearest neighbor calculation we just did, because it also reported to us the distance to the nearest neighbor. And remember here we ask for each cell, what is the nearest neighbor among the curve points? So using this here, I now get, if I now color each one by that, I get this here, and you can see these points here, the yellow points, they are really the points which sit right next to the curve. So the curve goes through this yellow part here. The green ones are those which are a bit further to the curve, and the blue ones are those which are so far from the curve, you notice with the logarithmic axis, right? It doesn't really make sense to look at them. This also justifies us in ignoring these here for the moment and focus only on those which are here greenish. And now, the thing I want to concentrate on today, what can we do? We want to understand what changes. And in the cells along this. And one thing I can do is that I pick a gene and ask what is this gene's expression along the pseudotime. So here in this plot, every dot is a cell. The x-axis is the cell's pseudotime, so how far along the curve it is, and the y-axis is the cell's expression strength. And the color tells us how close the cell was to the distance. And as you see, I only kept those which are reasonably close. This was this expression thing that we did last time with log k over s times 10 to the minus 4 plus 1. So it's this thing. This is our y-axis. And the x-axis is, as I said, the pseudotime, now normalized at the beginning of a point is 0 and the end is 1. And as you can see, this gene, which we have picked here, this is GLAST, that's the marker which they use to find, to recognize the stem cells. That's very strongly expressed in the early stem cells, and then it goes rapidly down, and then it's here at the bottom. I had to do a little trick because there's quite a lot of cells where this gene has an expression of 0. And now with this formula, of course, the 0 gets mapped to 0, so I have just one big line of zeros. And I wanted to be able to see how many cells are actually here on this line. So what I've done here, I first show you how it looks without that. Now you see all these lines with 0 on top of each other, and we have no chance to see how many points are here plotted on top of each other. This is why I introduced this little thing here, which says, if the expression is greater than 0, leave it as is, but if it's equal to 0, replace it with a random value somewhere between minus 0.2 and 0, so with a random small negative value. And that allows me to now here see, because it's now spread over this band, to see how many values are 0. And you can see here there's really much more values are 0 than having some value. And here it's the same. The density of 0 cells agrees here. And what we will now use, and I will explain in a moment how it works, is a technique called local regression. And what this local regression does is it produces this plot here. This purple plot, this magenta plot, which you can see follows through the middle of the line, but here it has treated the zeros properly, because our issue is, if I want to calculate somehow the average expression, averaging over all the points, and I average here on this strange scale, when how the zeros are valued corresponding to all the others depends on what scaling factor I here have, whether it's 10 to the minus 4 or something else. And this is very unfortunate, and we will now see a way how we circumvent this whole problem. And then we get here this very linear decay and going down here. So this purple curve here really follows this line, and we can really say here the expression is on average lower than it is here. And we will see in a moment here in this other write-up how this works. But for now, let's simply say, what can we do with this to finish this side of the story? I can do this not only for one gene, but for many genes. So here, what I've done here now is that I've run this log fit function that I've used up here for a list of 10 different genes, namely the 10 most variable genes that I had here. And for each of them, I calculated the expression along many different points here. So I get many such lines. But if I now were to plot 10 lines on top of each other, you couldn't recognize anything, because you see 10 lines with hard to distinguish colors. So the good way to plot this is to replace the lines with what we call a heat map. And here you see how this works. With the first gene, second gene, third gene, fourth gene, and the x-axis is the pseudotime. And the color simply tells us how strong the expression is. So we have turned the y-axis into a color axis, so that the y-axis now gets free to show us several genes. This is called a heat map because the traditional color scale makes it look like glowing embers. But here you can't see much because you see this gene here has a maximum expression which is much lower than this gene. So maybe I should change my color scale so that each row in this matrix here is divided by its maximum, so that each one goes up to 1 and down again. And that's what I've done here. I take these fits and I divide them by my maximum. And now you can see this here is a gene which goes down. This also goes down. This gene here goes up and down again. This also goes up and down. It's helpful to sort the genes in some useful way, and one easy way to sort the genes is to calculate the center of mass, so the average expression of each of these cells here, and sort by this, and then it looks like this here. So you can see, besides sorting, I also changed the color scale from the reddish to the bluish one, just because I like that one better. And when I now rerun the code for not 10 genes, but 100 genes, and then I got this plot here, which I show you better on the here, because here it's easier to see. And here you can now see for these 100 most variable genes, which I have now, for each of them, I made a smoothed curve like that one. And then I display this smoothed curve here as a color bar. And we can see how many of these genes are only active in the very early cells, in the quiescent sleeping stem cells. These are the genes which go up in expression when the cell wakes up from its slumber. And here are the cells when it starts dividing along the cell cycle. And here are the cells which are genes which are high in neuroblasts, and these are finally the ones which are high in final ready-made neurons. And even if you cannot really interpret all these gene names, you can see how useful this is, so that our rather complicated data set has now finally been brought into an overview where we can read from this plot a lot of information about what happens in which stage and how we get to these different stages. And we will come back to this, but before I talk more about this heat map, I should probably talk about how this line here was actually calculated, because there's a lot to be said about this, and all this runs under the heading of smoothing. Smoothing in practical data analysis or in statistics means you have a point cloud like this, and you want to find a line through it. And how do you find a smooth line through all these wiggly points? And as the term smooth says, we want this line to be not too wiggly, so to be have not too much second derivative. And for this, I've prepared that part here. The smoothing, this whole thing is titled smoothing, and it will show you several ways how to do smoothing. And smoothing is an absolutely essential technique in very many areas of scientific data analysis, so it's quite worth knowing a bit about this. And what I now do is here I have produced a plot which looks like this. So this is a function which takes a value from x and produces a value y here. See, it's a normal little continuous and a differentiable function, and you might wonder, how have I specified this function? Because I didn't want to use something useful like sine or cos, but something unusual, so that we have features like medium slopes, steep slopes, low slopes, sudden breaks, and so on. What I've done is I placed a couple of points on this thing and used something called a spline fitter to draw these lines through it. If you've ever worked with Illustrator, you might know this thing, this feature where you put a couple of points, and then Illustrator will draw a smooth line through it, and when you move the line, you will see how the points also move. Everybody knows what I'm talking about? Your document. Or let's say you have a function like, which one is it here? And now you can tell this thing, stop. I want it to be this here. That's what I meant. I have points and I get a smooth line through them. This is called a spline, and we will come back to them because I already used the spline logic here, but I haven't explained it yet. That comes at the end. So this is our example function. And now let's imagine we have some complicated apparatus or system or cell which reacts to stimulus. So we can make experiments with this thing by putting some input data, subsetting on a dial, and this is the output, how it reacts. Physics is full of such examples that you have a system where you put something in and then it produces a reaction. And we imagine that we cannot measure the reaction perfectly, but we have a noisy measurement. So when we measure that, what we then get is something like this here. For a given x value, I get not the actual y value that the curve says, but the y value plus some added noise. How do I simulate this? Here you see I started off by just taking 100 randomly distributed numbers, which are all between 0 and 1. This here means you draw n uniformly distributed numbers between 0 and 1. The seed I set so that it will always draw the same values no matter how often I call it. Do you guys know about pseudo-random number generators, which iterate a formula and you need to have a starting value? Okay, so I guess you've learned about random seeds. This is my random seed. And now I get here my x values. And for each of these x values, I calculate the corresponding response by running it through this function here. And then I add a bit of noise to simulate the fact that my measurement doesn't give me the true value, but a deteriorated value due to measurement noise. And if I now do this, I get this plot here, where I can still see the curve, but it's not so clear anymore. Now my task is, can I get back to this original curve by finding a smooth curve which goes through the middle of these dots. The simplest thing that we can do is bin means. We just divide up the x-axis into, say, 10 bins, all each of size 1/10, and we just take the average of the y values in each of these bins. And if I do this, what I then get is this here. And you see, for the bins between, for the first cell, the bin is here, for the second it's here, and so on. And you can already sort of see our original curve, but it's rather rough. I could make it finer by making the bins finer, but then each bin would only contain 2 or 3 points, and averaging over them will produce too much view noise. So this binning is too primitive. Let's do something better. And the most widely used standard method is called kernel smoothing. Kernel smoothing works as follows. For each possible value x for which I want to get a point value, so let's say I want to find the value of my smooth curve at position 0.25, I calculate the weighted average of all the y values around this, as I've done before, but I weight I do not make a rough bin, but instead I weigh each point according to how far it is from the point which I want to calculate. So I want to calculate the value of my smoothed function at position x0. So I check how far is this from x, and then I use a kernel function, and kernel function in this context means always a function which looks like this, with a bump around 0. And if I now take the distance of my for each data point, I ask, oh, there's an I missing here. For each data point, I ask, what's the distance of this data point to the position for which I currently want to calculate the smoothing value? And I divide this by some width of this thing, and then I get a weight. So if I have points like this, and I make a smoothing curve like this, to make this smoothing curve, to get, for example, this point here of a smoothing curve, I put a kernel over this one, like this, and this kernel, which is centered around that thing, will now tell me the weight of each of the other data points, and I weigh each data point with this weight and take the weighted average. And if this thing has a support going only from here to here, only the points within this kernel will contribute to my average, while these out there will get a weight of 0. So that's what I've done here. I say to get the point at value x naught, I take the average of the function of the data y values of a data, each data point value weighted by some weight value w, which depends on how far the data point is. That here's an I missing, how far this data point is from the point where I currently want to calculate this. And now I need a kernel, so anything which has roughly a shape like that one. And what people really like to use is this one here. It's called the tricube kernel, and you see it has a couple of nice things. First, it is differentiable, so you can get a second and a third derivative. It smoothly goes to 0 exactly at -1 to 1, so you can say everything between -1 to 1 will influence the value and everything further out not. And on top, it's a bit flat, so that it sort of naturally puts similar weight on everything which is in the middle and then lets the weight smoothly fall off. So I use this one here, and you see it's just weirdly constructed to look like this. People just played around with this.
A lot of these kernels that you mentioned in the script as well have support for U less than.
Yeah.
But does that suppose that you have some normalized distance?
Yes. And this is what we have here. This is the h. You see, this thing has support on -1 to 1, which we change by this rescaling into a support from x naught minus h to x naught plus h. So a window of size 2h around the point which we want to look at the moment. And this is what I wanted to show here by this. I have my data point and I put this around that one up. So we use this kernel here, which we define to be 0 when we are further than 1 away. And I have defined this function here. And now you can see how the smoothing function works. I ask what's the value of my smoothed function at position x naught, and what it does, it calculates weights by subtracting from each x value of every data point, scaling all the x values of a data point around the desired point, and then it calculates here the weighted mean. So the sum of this, the sum of the weights. And to do this now, in practice, what I do, I calculate my tricube kernel, calculate here the smoothing function, and now I calculate here a grid of values. Just I split up the area from 0 to 1 in 300 steps, so that I have now 300 numbers that smoothly equally divide up the unit interval. And for each of these values, I call the smoothing function. So each of these 300 values I insert here for x naught to get a corresponding y value. And that's what I do here. The sapply is a way in R to say, take each of values in this list of values and put them into that function. And this function, as you see, has, besides this x naught, it has 3 further parameters. Putting for the remaining parameter here x, the x values of our data points, the y values of our data points, and put the smoothing bandwidth to 0.1. If I do this, then I get for each x value a y value, and I can plot them against my slowly increasing x values, and then it looks like this. Here, the red crown is our curved, is our smooth curve. The black ones are the original data points. And just for good measure, I also added the blue line, which is the data, which is the line from which we got the original data. But of course, our task is not to make a line fitting the blue line, but a line following the data points. And you see, it follows the data points quite well. And again, the way how it works, the value of a red curve, for example, at 0.8 was calculated by putting a kernel from 0.7 to 0.9, because the bandwidth was 0.1, so from 0.8 minus 0., and use this kernel, so we scale our tricube kernel such that it sits here, and use this to give a weight to each of the data points here and calculate the weighted average of the data points here. Questions about that? So, and if you look at it, it seems to work quite reasonably well, except up here, because here it seems that these points here, they couldn't pull up the average enough because the average gets pulled down so much here. And by I, we have a feeling that there's an upward slope here and a downward slope here, but our average spring procedure, of course, doesn't see that. Maybe before we go with yes, the bandwidth choice I should talk about. So here you see the smoothing function with a bandwidth of 0.1. Now what happens if I increase the bandwidth maybe to 0.4? And as you can see, now we always average over the value minus 0.4 plus 0.4, so we average over half of all the data, and so it cannot really follow the minute details anymore. I can also try 0.2. Now it sort of still works, but this point here is now an average of all the values from 0 to from here to here, 0.2 in both directions, and even for those at the wings have low weight, we still have high weight for all these here, which makes the whole thing pretty imprecise. So if we make the bandwidth too large, then we average out small details of our data. If we make the bandwidth too small, for example, like this here, then as you can see, there will always only be 1 or 2 data points below every kernel, so we don't have anything to average over. You can also take 0.05. And as you now can see, this sort of works. Now there's always 0.05, there's always maybe 5 of them, but you see the line becomes too wiggly. And it tries to follow all the individual data points. We don't want that either. So we can look around and try to say maybe 0.1 is okay. But low adaptive bandwidth I come to later, or I can talk about this already now. You can see there's areas here that I deliberately have done such that sometimes the data points are closer to each other. In some areas they're a bit more spread out. So maybe we should make the bandwidth smaller wherever we have much data and wider where this isn't the case. We'll try this in a moment. But before I do this, I want to look at something else. Here, if you look at the red line, it's, as I said, it can't really follow this step here. And maybe we could do a better job by allowing the regression to also get a feeling not only for the absolute value, but also for the slope, that it sort of senses how this goes up here and down here. And the way how we can do this is using local regression. And I show you how local regression works. In order to find, say, the value of our smooth curve at this point, we take all our data points around the kernel bandwidth, and here you see I have now drawn them by making the size of a data point proportional to their weight. And before we simply said now we make a weighted average of all these values. But what we can also do is we just make a linear regression. So we fit a line through it to follow a least square criterion. A linear fit with weight works as follows. You know, in an ordinary linear regression, you make a line through it, and then the optimal line will be the one which minimizes the squared this vertical distance of the data points to the line. And here it's the same. We minimize the squared vertical distance, only we multiply each distance with the corresponding weight. So this is what we call weighted regression, and you see here is what we do. Y hat is the value, let's say A and B are intercept and slope of our line, when yi hat is the position on the line at a given x position for a given data point, and this here is the deviation, the squared deviation in vertical lines of the fitted value to the, there's again an I missing, to the data value. And this thing is now, instead of saying this thing should be minimal, we say the weighted sum of this should be minimal. So, and then we will later see that we can still fit such a weighted regression the same way how you always fit a regression using the normal equation that you might have seen before. So what I now do here is, I now, as I said, I pick one point. Let's say I want to calculate my smoothed curve's value at point x naught is 0.4. Here I calculate my weights according to the kernel and plot this. And now I make my linear regression by simply saying, make a linear regression of the data points of the y coordinates of the data points onto the x coordinates, weighting each data point by w. And then we get this result here, which is the result which minimizes this modified least square criterion with this intercept and this slope. And if I put this in, this is the orange line, and at the position x04, we have this, we go through this red circle here, which is the circle at the point on the orange line where it goes through our query x value 0.4, which we called x naught. And I can do this for every query value. So I again take my grid of data, and here you see I've put together the function that I've just described to you in order to get the value that the smooth curve has as a position x naught, given data points xy and a kernel bandwidth h. Calculate first the weight, then run a linear regression with these weights of the data y on the data x, then take the equation of our fitted line and calculate the value of this equation at the query point x naught and return this value here. So it doesn't return the whole line, it only returns the y position of this red circle. And again, I use my sapply to say, call this function for each of my 300 values that I have, with which I have divided up the unit interval. And so I get then 300 new values, and now I get this red curve here, which is slightly different than the red curve I had before. And this is now what we call smoothing with linear regression. Or people like to call it, the guy who originally came up with this thing called it lowest smoothing, for locally estimated or weighted scatterplot smoothing. That's how it was called in the paper which came up with this method 40 years ago. So many people call it less or lowest smoothing. Other people call it local regression. And as you can see, this is how it works. It doesn't look that much better as before. It still hasn't really fitted this. But once I have decided on this, I'm no longer bound to really plot only a line. Instead of plotting a line, I can also fit a parabola to go through these values here. Again, doing the least square criterion. And this will be very useful because if I put my value up here, the parabola will really hopefully do a good job following the curved shape of the line. So what I now do is I quickly change this function here and tell it, instead of fitting a line, fit a parabola. And this is very easy to do in R because I simply say here, regress y on x and x squared. Where was it? Here. This is the same function as we had before, except for the thing that I now say y should be regressed on x and on x squared. R has a strange way of interpreting these formulas with a tilde. It understands a square usually as a fit on all combinations of this to means no literally fit on the square of this value. I have to put this I in front, but that's just a minuteness of our syntax. And this fit function will now give us the three variables for the three coefficients for our parabola equation, a constant intercept, a linear term, and a quadratic term with the corresponding coefficients, and it will return these. And again, I do the same as before. I call this function, putting each of my 300 grid values for x in here, and then I get the red line. And as you can see, this now works quite reasonably well. Here, this line goes down a bit, but it doesn't go up. And what I can also do in R, there is this function logfit, and this logfit function, I can tell it that it should do exactly what I've just shown you here. So logfit or lowest, you simply tell it y against x. I want second degree, so I want parabolas, so a second degree polynomial fitted locally, and the span takes the place of the bandwidth as before. So, but I made now, hey, I switched over the adaptive bandwidth already. Sorry. As you can see, the lowest function gives you slightly different values as a red one. I never figured out why this difference is, because in principle, my formula here should do exactly the same as lowest. What I've just accidentally skipped over here is the adaptive bandwidth. At the beginning, when I got my example data, I chose, as you remember, I chose here at the very beginning, I told it to choose 100 data points and choose 100 x values uniformly from the unit interval. But what if the x values are not uniformly distributed? Yes, it's a higher order adaptive bandwidth here. So I do the same as again, I fit let me switch here to adaptive bandwidth. I get my x values, and this time, as you see, I've taken my x value not from a uniform, but from a beta distribution, or from two beta distributions, such that I get very many values in the beginning and the end, and my values get diluted in the middle. And now our standard fitting function will not do a good job. If I do now here my quadratic fitting function that I've just shown you, this one here, I haven't calculated all of this, then it does a bad job here, because the bandwidth that I've chosen, 0.1, is quite appropriate here and here, but it's way too low, too small here, and hence here the bandwidth always only captured one distance. And there's a simple trick to go around this, which is called adaptive bandwidth choice, and that simply means whenever we do a smoothing for a certain x value, we calculate the bandwidth such that we rescale the width of our kernel such that exactly, say, 20 points are under the kernel, or exactly 10 points are under the kernel. And to do this in practice, what I do, I now change here my quadratic thing with the adaptive kernel by first calculating the distance of each data point's x value to my desired x naught value, where I put the middle of my kernel, and I sort by this. And now let's say I want to have always 40 under it, so 20 under the left wing and 20 under the right wing. Then I simply ask, what is the distance of the 20 furthest data point? Or wait, I put it here with absolute value. So if I now were to sit here, and let's say Hn has 10, so we sit here at 0.5, when we take the distance of each data point in x direction from our query point, take the absolute values and sort them by the distance, and then find out maybe the 10th widest data point has the distance 0.15. And then we know that if we make the kernel with 0.15, then the support will exactly cover 15, will cover the 10 data points who had data up to that value. So that's what I do here. I sort the distances of the data points to my query point in x direction. I pick the 10th closest data point and say the distance to that data point should be my kernel width. And then I do my fitting, and that will cause that within that here where the data is sparser, it will take wider kernel bandwidths, and here where the data is dense, it will take small bandwidths. Make sense? So, and yes, and as I said, in R, of course, there's a ready-made function. There's a function called lowest, which is always part of R, and there's a slightly improved function called logfit, which has a lot of extra functionality. And here I call this lowest function to do the same as my local quadratic regression. I also tell lowest, please make fit quadratic polynomials, and please make the bandwidth such that always 30 points are under my kernel. Span has to be put as a fraction of all the data points. This is why I divide by x, so that it says I want 1/10 of all data points under my kernel. And when we get this thing here, and in principle, LÖS should do exactly the same as what I've described up here, but at this place it has done something different. So maybe LÖS has some extra penalization against this wiggliness here, which is missing in my code. But in principle, it should be the same. So now the next question is, how do I know whether the red line is close to the true function? Because normally I don't know the blue function. And the first thing I can do to this is called bootstrapping. Anybody ever heard of bootstrapping? Okay, for the others, bootstrapping is an idea, I think, originally by Efron, who is one of the fathers of high-dimensional statistics, which works as follows. Imagine, maybe I demonstrate bootstrapping because it's a really neat concept. First, with some arbitrary example data. Imagine I have some plot R norm 20. What should I do here? I want to skew it a bit. Yes. Let's say 20, 10, 1 to the 1.5 power. So here I have now made a data point, and as you see, this is not normally distributed. I put a power so that everything is skewed to one side and not to the other side. If I do this with 200, then you can see, you can't properly see because that's too little. Let's make it like this. Yeah, now you can see most of the points are down there, but at the top there's a few outliers which are sparse and go high up. Oh, sorry. And I want to calculate the mean of these data points. And let's say this is my data that I have, and that's all I have. And I have plotted a histogram of my data and have noticed this does not look like a normal distribution. And now I calculate, say, the mean of this data, 327. And I want to know how precise this mean is. I could do the usual, let's take the square root of the data, let's take the standard deviation of data and divide by the square root of the number of data points and say, okay, the precision, the standard error of this mean should be plus minus 6. But maybe I'm unsure whether this formula is appropriate for such a skewed distribution. Actually, it is. This formula doesn't need the data to be normally. It works also for skewed stuff. But imagine you do some estimator where this isn't the case, and you're not quite sure how well you estimate this. What you can then do is you can try out what would happen if what I now can do is the following. I can get new data and can calculate again the mean of the new data. And I do this a couple of times. And now, of course, I can see how much the mean scatters. And if I did this 1,000 times, I could make a histogram of that, and then I would get the sampling distribution of my mean estimator, so I could see from that how precise I can estimate the mean. However, this is a theoretical exercise because I've just been cheating. I said I just get new data. I can do this because I simulated my data, so I can just rerun the simulator. In a real-world scenario, you're given your data, and you've made some complicated survey or experiment, and you got your 200 data value, and that's all you have. Going out and repeating the experiment 20 times is not an option. So you want to get new data without getting new data. And that's where Efron came and said, yes, what we really would want to do is to sample again from the underlying true distribution, as I've just done it. But we don't have the underlying true distribution because it's empirical data point. The second best thing is that we sample from the data points we have ourselves. Sampling from the data points we have ourselves means we just say, if this is our data point, then the most straightforward estimate for the underlying distribution is simply a probability mass function which has a delta on each of these values and nothing anywhere else. And sampling from this means picking a data point from this probability distribution, which actually means picking a value from one of the values of x. And if I now want to resample 200 new data points, I have to always pick this, and here now I have to say replace is true to make it clear. Always pick 200 times, pick one value out of the data, a random value, but there's nothing wrong with picking the same value twice. So we replace the value back into back with all available values after having drawn one. And so I get this here, which is now my bootstrap sample. It's my attempt to sample from the straightforward empirical estimate of our distribution. I can calculate the mean of this here. And this I can easily do often, and I can see how much my mean changes here now. And this is a perfect way because it's universal. Even the mean is the simple estimator. For the mean, the sampling distribution is always normal, and it always follows this function, this formula here, or at least it's close to normal. But if you have some estimator for a standard deviation, or for the upper quartile, or for the median, or for something else where you don't have a closed form solution, where you might not even have a closed form solution under the assumption that your data is normally distributed, and where it gets even worse if you have reason to believe that your data is very far from normally distributed, then maybe this might be the best way to get a decent estimate for the standard error of your estimator. Because no matter what you have, it might be a very complicated procedure that you have to do with your data, where you came up with a complicated analysis plan where you have to do this step and that step and that step with your data, and then in the end you get a value and you want to know how precise this value is. When you take a new bootstrap sample, by pulling values from your sample with replacement, and repeating this 100 times, always run through your whole procedure, and then you see how much the result scatters. And that's when the precision of your result. The catch is the true underlying distribution here is probably something like this, with whiskers, with tails which are most likely a bit further out than you see here. The true distribution probably also has some probability here and some probability here, because it's unlikely that our actual data really contains the smallest value which is at all possible, like has non-zero probability in our distribution. It makes sense that if we actually did redo the experiment, it's quite likely that we find a value which is a bit further out here or a bit further out here. So essentially, with everything, if we resample from this data, we are constrained to get data from within this interval, even though we know that redrawing real data would give us something from a broader interval. So in a way, our resampling procedure, we know that our empirical distribution is too narrow. And our bootstrapping procedure underestimates the variance of the data and therefore also the variance of the estimator, which means in practice, when you do this bootstrapping procedure, it's an approximate result. It could be that the real uncertainty is 50% larger. If you're unlucky, maybe it's even twice as much. But you can be absolutely sure that it's not 10 times or 100 times as much. So bootstrapping is a great way to get an order of magnitude estimate for your sampling error, or maybe something which is precise up to plus minus 50%, but it's not perfect. But for surprisingly many cases, this is actually good enough. So this was just a short look at modern statistics. And now let's use this bootstrapping procedure here for our fitting example. What I do is, I have now said I use the kernel smoothing method, so the very first method. And I use it on my bootstrap sample. To do this, I have to be a bit careful. I can't do what I've just done here and say sample from my list of data, because I have two data vectors, x and y. So what I do instead is I say sample a value from one to out of a list of all of them. So the sample int function works as follows. Sample int 10, 100, replace is true. And you see it gives us, it just always draws one value between 1 to 10, and then again a value between 1 to 10, and replaces true means the probability of each value is always 1/10, no matter how often you have already drawn the value before. And now I can use these here as indices in my data point. So I can already see what this means, that the 10th data point, for example, will appear 4 times in my sample. Now in practice, I draw exactly as many data points as I had originally, because I want to resample my data. So if I want to get a resampling from what I have here, a bootstrap sample of my data, then I have to draw a new data sample which has exactly as many data points as my real data. So if I have a real data of 100 data points, then I should draw a bootstrap sample which also has 100 data points, which means it's unavoidable that some data points will appear multiple times and some data points not at all. Because if I said each data point should appear exactly once, I wouldn't have a bootstrap sample. I would just keep the data points that I have and nothing would change. So this is why bootstrap sampling always has this thing that you sample as many data points as you have. Here you don't even have to write it twice, it does this automatically with replace is true. And then I can do this here, which means take the values from x indexed by these indices, and here the values of y indexed by the same indices, and then I get here my bootstrap sample of x and y. And I run my kernel smoother on that, and what will now happen is if a kernel smoother now gets one data point twice or 3 times, then of course this data point will always have triple weight because it appears 3 times in all the sums. And what I've done here now is I ran this bootstrapping procedure 100 times and hence drawn here 100 red curves, which each show the possible smoothing procedures which could come out. And this now gives me a pretty good idea of how precise my smoothing works, how well I can approximate it. We see immediately that over here the shape is quite clear, but we can't quite say the line goes down here or here, it moves a bit. And here, of course, when the data is wide, it's a bit imprecise. especially as I ran it here with our very first function, the kernel smooth, which doesn't have any, which didn't have any adaptive bandwidth. Here I now do the same, allow with a quadratic regression, where I also allow to fit not only a line, but also a parabola, which looks like this. And did I also add the bandwidth? No, this is without this. Yes, this is using the loss function, so it uses adaptive bandwidth. And here you can see this now works quite well. Of course, here the uncertainty is a bit higher, and here it's a bit lower. So this is one way how to see how well smoothing works. And we can see it didn't work perfectly because the blue line doesn't quite follow this thing, but everywhere else it seems to work reasonably well. Of course, the fact that it can't follow the blue line here is simply because the data points which we have drawn all happen to be below the blue line. So it's correct that the smoothing thing, because it only can work with the data we give it to it. But overall, this works. There's other ways to do smoothing. And one more way to check the uncertainty of it, and one more way that I want to mention is called leave one out cross-validation, which works as follows. For each data point, we ask how would the smoothing curve be if we removed this data point? And so the red point is basically if I calculated a smoothed curve, so I take a data point, for example, this one, and I ask, if I calculated a smoothed curve, which through all my data points, but I leave this data point out, where would the line go through the x position of this data point? And the answer is here. So that's what I've done here. For each data point, I put a red point at the x position of the data point and at the y position that the smoothing curve would have if we smoothed with all the data except for this data point. And this basically is a good way to tell us how much the data depends on the individual data point and how much the individual data point influences the overall smoothing. And you get this red line here. The last thing we can do, which I don't want to get into detail now, but if you remember, if you've ever learned a bit more about the mathematics of linear regression, you might know that the linear regression gives you a standard error for each of its coefficients. The same way how you can say the standard error of a mean is the standard deviation of the data divided by square root of a number of data points. You can also calculate this for the coefficients that come out of a linear regression. And using these, you can also get a standard error for the actual y value that the thing predicts for the curve. And I ask here now, I run this thing and I ask it, give me these standard errors. And now I draw my fitted curve and add and subtract the standard error to the curve to get this pink band, or this ribbon, we call it, this pink ribbon, which tells me what the math of a linear regression tells me about what the plausible areas are that the blue line might be. And you see, this works quite well. The blue line actually stays within the pink ribbon. So, it's 4:30. Now that thing I will go into next time, but I haven't managed to reach the point, which was actually the crucial idea here. How do we deal with the zeros? Because all the smoothing that I've shown you so far, if we give it these data points, then the shape of a smoothing curve will depend a lot on the distance between the value we give for the zeros and for the non-zeros. And you remember the zeros actually would have minus infinity because we have here a log scalar, but we lifted it up from minus infinity by using our pseudo count. So we actually lift them to the logarithm of 10 to the minus 4. If we had a lower value here, like 10 to the minus 5, then this ribbon of zeros wouldn't appear at -4, but at -5, further down. That it isn't at -4, by the way, is because Serra doesn't use a decadic logarithm here, but a natural logarithm, so everything is shifted. So the distance between the zero and the non-zero depends on this arbitrary scaling factor. And that means, and this of course influences the curve. If I now do the curve with my smoothing, I can do two things. I could either say, let's fit the curve on the natural scale and take the logarithm afterwards. But that's not a good idea, because on the natural scale, the strongly expressing genes like those up here will have much more influence on the average than those down here. Simply because, you know, if you have 3 cells, one has expression 1, one has expression 10, and one has expression 100, the average of these 3 values will be 95 or something like that. What we want is a geometric average, where we say the average of 1, 10, and 100 is 10. So we want to take our average on the log scale, so that the line goes through the middle of the data on the log scale. But if we did the fitting on the natural scale, it would stay up there at the highest points. To make the data go through it on the log scale, we should first take the log and then fit it. But if we first take the log and then fit the data, then we will notice that the shape of the curve will be influenced in an arbitrary manner by this gap, which stems from our arbitrary scaling factor. And now here it turns out that we can get around the whole thing by taking advantage of the fact that we know our data is Poisson distributed. You see, so far in all our smoothing, we used a least square criterion. As you might remember, here for all this local fitting, we always said make an ordinary least square regression. And ordinary least square means the distance of the point to the red line weighted by the kernel should have a minimal sum of squares. Now, why do we use least square? In this case, we use least square because our whole model at the beginning was assuming that our noise is normal. You remember this was our data. We postulated that we have some machine where we put in the x value and it delivers us the y value according to the curve with a normally distributed noise added to it. And this is the implicit, the unspoken assumption that's done in all linear regression. We use linear regression with the least square criterion because we assume there is some real truth from which we deviate due to the addition of a normally distributed noise. And we furthermore assume that the standard deviation of this noise is as high here on top as it is down here at the bottom, because it's additive noise. We always just add one amount of noise. Noise can either be additive or multiple. Well, it can be a lot of things. But the two most basic kinds of noise is additive noise, where we just add always the same scale of noise to it, like we have it here, or multiplicative noise, where we say we multiply our data with a factor somewhere between 0.9 and 1.1. Which then would mean that the spread up here on top is wider than down here at the bottom. So it is important to check whether the amount of noise depends on the mean. And here we can see that the typical spread of a data point is independent on the typical average of a data point. So the standard deviation here, of this data here, is the same as the standard deviation down here. Statisticians call this homoscedasticity. Homoscedasticity means within your data, the variance does not depend on the mean. The opposite is heteroscedasticity, where the variance typically seems to increase with the mean. And this is what we have in our count data, because we know that in Poisson distribution, the variance increases with the count data. And that already gives us a hint of how we can work. If we have noticed that the variance is proportional to the mean, for example, we can also say that the weight should undo that by down-weighting the samples with high variance and up-weighting the samples with low variance, because we want to up-weight the precise samples which are precisely measured and down-weight the imprecise samples. This means that we have to predict according to the mean value that we estimate here, so to a value where our right curve sits. We predict what the mean should be and which variance we therefore expect at this level of the mean, and use this to adjust our weights. This procedure is called iterated reweighted least square. So we make an iterated fitting where we always change our weights according to the mean that we have predicted, and we assumed mean variance relationship. And once you use this, you go from your linear regression to something, from your linear model to something which is called a generalized linear model, or GLM. And the nice thing about GLMs is that they can accommodate non-normal noise. They can work with noise which is not normally distributed, but for example, Poisson distributed. And it does this by using this trick that I've just said, that it uses the variance mean relationship to reweight the terms in our sum of squares. And this is a very crucial technique whenever you work with count data, because in count data you don't get around noise. So next time we will see in general how this GLM fitting with IRLS works, and then we will see how we use this for smoothing, and then from that we will go down here. Eventually, in maybe 2 or 3 weeks, we will then come to the conclusion that this even affects our PCA. The PCA, we also had a least square criterion, which we thought is appropriate, but it suffers from the same thing, and we should modify the PCA in the same manner. And when we get to something which is currently very fashionable, because it's one of the standard textbook examples of a deep neural network, namely an autoencoder. And that's why I want to go in a bit more detail here, because this whole using the proper function replacing the least square criterion by, as the machine learning people say, by the correct loss function, is something, is sort of something at the heart of the use of neural networks and of machine learning in general in all these different, AI is of course not trendy, but we always have to put it in. And I think it's really important to understand the basics of neural networks, no matter whether you want to use it for biology or for something else. And one of the basics is hidden in what we've just talked about, in this adaptation of the, in this knowledge about the measurement process and its noise distribution in variance mean relationship. But we'll get into this next week. If you're curious, you can of course already skip ahead here in what I've already uploaded. So, questions, remarks, other points about that? Otherwise, we can see, we'll talk tomorrow about the exercises, and next Monday about how we get back from this long detour to smoothing functions back to our biology and to our heat maps here. And then also to the principal curves, which are also this thing here, what I said at the very beginning, how do we fit a curve through all these data points is of course also a smoothing question, only this time it's not a 2D smoothing, but a smoothing in high dimensional space. But we will see that it's essentially the same idea again. Okay, so thanks for your attention and see you tomorrow or next week.